Okay, students, good morning. And now, in continuation with the video lecture based on thermal properties of matter, that is chapter 11 of class 11th physics, we are discussing the in the previous video we had discussed about various type of expansions, that is linear expansion, areal or superficial expansion, cubical or volume expansion. Now, proceeding further on this chapter, we had seen the relationship between alpha, beta, and gamma, and what we had observed that alpha is to beta is to gamma, that is equal to 1 is to 2 is to 3, or we can say that beta is equal to twice of alpha and gamma is equal to thrice of alpha. Now here we want to show that the coefficient of areal expansion, that is equal to beta, for a rectangular sheet is twice of its linear expansion, that is beta is equal to twice alpha. We want to prove over here. So look at here how we are going to prove that coefficient of areal expansion is twice of the linear expansion. So for this we are supposing a rectangular sheet. Look at here, this is the rectangular sheet, and it has, we had supposed it has length A and it has breadth B. Now on hitting it, obviously it will expand, and since it will expand, then suppose this expansion is delta A, and in this side also it will expand. So this expansion is what? This expansion is delta, this expansion is delta V. Now suppose this is area A, initial area A, then it can be written as delta A1, and it is equal to what? It is equal to A delta B. Similarly, it can be written as delta A2, and it is equal to B delta A, and it is equal to delta A3, and this is equal to delta A into delta B, because this is delta A and this is delta B, so the area A3 is equal to delta A3. Now we will see for the value of delta A what is the delta A. So obviously delta A is linear expansion, so it can be written as alpha into A into delta T, alpha into A into delta T. Similarly, delta B is equal to alpha into B into delta T. Clear? Now we have to find the change delta A1, and delta A1 is what? Delta A1 is equal to A into delta B, and delta A2, that is B into delta A. Clear? So now we are going to consider, that is change in area. So change in area delta A is equal to what? Delta A1 plus delta A2 plus delta A3. Look at here. So delta A1 is what? A into delta B plus B into delta A plus delta A3 is what? Delta A into delta B. Obviously, putting the value A into delta B is what? Alpha B delta T plus B into delta A, that is alpha A delta T, and alpha A into alpha B is what? Alpha A delta T into alpha B delta T. Now look at here. We can write it as alpha AB delta T plus alpha AB delta T plus alpha square AB delta T square. Now dear students, look at here. Alpha AB delta T, taking alpha AB delta T common. And if you are taking alpha AB delta T common, then 1 plus alpha into delta T, or we can write it as alpha AB delta T 2 plus alpha delta T. Now look at here students. If we consider, if alpha and delta T is very small. So if alpha and delta T will be very small, then look at here, the product of these two will also small. And if you are going to multiply over alpha into delta T here by opening the bracket, then it become alpha square into delta T square, and it will further very much small. And here this quantity is multiplied by 2 alpha T to 2 alpha AB into delta T. So multiplication with 2 increases its value. So this quantity is very small, and so alpha into delta T can be ignored. Alpha into delta T can be ignored. And if alpha into delta T can be ignored, then delta L will become what? Delta A is equal to alpha A twice of alpha A delta T. And now we can write it as delta A upon A delta T, that is equal to twice of alpha. And you know that what? Delta A upon A delta T, it can be written as what? Beta, and beta is equal to twice of alpha. So coefficient of superficial expansion is twice of the coefficient of area expansion. Now we will look for the anomalous behavior of water. Dear students, I want to add here that water has a specific behavior. So it is called as anomalous behavior of water. And what is the specific behavior of water? That if we increase the temperature of water from 0 degree Celsius to 4 degree Celsius, as you know that at 0 degree Celsius we find water in its solid state, and if we are going to increase the temperature of water from 0 degree to 4 degree Celsius, then its volume decreases and its density increases, and at 4 degree Celsius the water shows its maximum density. And when further we are going to increase the temperature, then the volume of the water going to be increased, and so its density starts decreasing. So this this behavior is apart from the general behavior of the matter, where with the increase of temperature the density decreases. In case of water, from 0 degree to 4 degree Celsius its density increases, and from 4 degree and above temperature its density decreases. So water shows its anomalous behavior. And what is the anomalous behavior? Look at this diagram. Suppose here on this axis we have plotted the temperature, and on this axis we had plotted volume. Then what we observe? We will observe that this is the graph. So this is the volume at 4 degrees Celsius, that is, you know that density is what? Density is equal to density, that is rho, and rho is equal to mass upon mass upon volume. And here the density is what? Volume is minimum, so density here, density is maximum. Density is maximum. This is at 4 degree Celsius. And after that, what you are seeing, that volume is increases, so density decreases, and from 0 degree Celsius to 4 degree Celsius, 0 degree Celsius to 4 degree Celsius, the density will increase, the density of water increase. So density of water, density of water increases from 0 degree Celsius to 4 degree Celsius, and at 4 degree Celsius water shows its maximum density, and above 4 degree Celsius its density decreases. So it represents the anomalous behavior of water. Now we are going to discuss about the next topic. Dear students, now look at here the question in front of you. So that the coefficient of volume expansion of a substance is 3 times the coefficient of linear expansion. Means here we have to show that gamma is equal to 3 alpha, and for this we will suppose a cuboid. We have to suppose a cuboid, that is it is what? This is A, B and C. Okay. Now what will happen if we increase the look here, with increasing temperature, so as the temperature increases, then the A will increase, that is A dash, that is A plus delta A, B dash B plus delta B, and C dash is equal to C plus delta C. Now dear students, as A, B, C and R lengths, so we can write it as delta A is equal to alpha A delta T. Similarly, delta B is equal to alpha B delta T, and delta C is equal to alpha C delta T. Clear? This is the value of delta A, delta B and delta C. C alpha delta T, B alpha delta T and A alpha delta T. Or A dash can be written as what? A plus delta A, as we had mentioned there also, and it can be written as A1 plus alpha delta T. Similarly, B dash can be written as B plus delta A and B1 plus alpha delta T, and C dash can be written as C plus B plus delta B and C plus delta D, C1 plus alpha delta T. Now its original volume V is what? Its original volume V is A B C. V is what? V is equal to A into B into C. Now V dash can be written as what? A dash, B dash and C dash. And on multiplying A dash, A 1 plus alpha delta T into B 1 plus alpha delta T into C 1 plus alpha delta T. And we can write it as A B C 1 plus alpha, this is capital T because we have mentioned it there capital T. So this is capital T. So A B C alpha delta T. Now dear students, here we have to find the change in volume, that is delta V. So delta V is equal to what? V dash minus V. So it can be written as V dash minus V, and V dash minus V means it can be written as ABC 1 plus alpha delta T whole cube minus ABC, and taking ABC as common, it can be written 1 plus alpha delta T whole cube minus 1. Clear? And it can be written as delta V upon V, because ABC is equal to V, and it is 1 plus alpha delta T whole cube minus 1. 1 plus alpha delta T whole cube minus 1. Clear? Now coefficient of volume expansion. Coefficient of volume expansion, that is gamma, and it can be written as del V V delta T. Del V V delta T. So del V upon V. We are knowing the value of del V upon V. So it is equal to 1 plus alpha delta T cube minus 1. 1 plus alpha delta T cube minus 1 upon delta T. Okay students, this is the value of gamma. Now what we will do, A plus B the whole cube, we will apply the formula for A plus B the whole cube. So gamma can be written as A cube plus B cube plus 3A square B, okay, plus 3AB square minus 1 upon delta T. Okay, you can write here. And for the small values of what? For the small values of alpha and delta T. For the small values of alpha and delta T, we will ignore the higher values. So for small values of alpha and delta T. Look at here students. I am writing from here. For small values of alpha and delta T. For small values of alpha and delta T, higher powers will be neglected, so this term will be neglected and this term will be neglected. So gamma will become what? Gamma will become, and 1 to 1 cancel out, and it will become 3 alpha delta t upon delta t. Okay, and so delta t to delta t cancel out, and we can rewrite it as gamma is equal to 3 alpha. Gamma is equal to 3 alpha. So this is the relation. So before that we had proved gamma is equal to 2 beta, and here we had proved gamma is equal to 3 alpha. Means coefficient of volume expansion is 3 times the coefficient of linear expansion. Clear, students? So this we had done nothing. We had calculated the value and relationship change. We had calculated del B upon V calculated, and del B upon V we had put it in it, and from here we got the value of gamma. Clear, students? Now we are going to discuss about the next question. Okay, dear students, look at here another question in front of you. Suppose the question is saying that a hole is drilled in the copper sheet. There is a copper sheet. Suppose this is a copper sheet and a hole is drilled in the copper sheet. The diameter of the hole is 4.2 centimeter. The diameter of hole, it is given that 4.24 centimeter. Okay, it is given 4.24 centimeter. At 27 degrees Celsius, initial temperature is 27 degrees Celsius. What is the change in diameter? We have to find out d2 minus d1 change in diameter when it is heated to 227 degrees, when it is heated to 227 degrees Celsius, and coefficient of linear expansion it is given. Alpha, value of alpha it is given. So coefficient of linear expansion it is given, so we can find the coefficient of areal expansion. Coefficient of areal expansion, and this is equal to beta, and beta is what? Twice of alpha. So twice of alpha it is given. This is the value of alpha, linear expansion. So 2 into 1.70 into 10 to the power minus 5 per degree Celsius, and on multiplying it we will get the value 3.40 into 10 to the power minus 5 per degree Celsius. We have got the value of beta. Now diameter, initial diameter it is given. So initial area A1, initial area at 27 degree Celsius, that is A1, and it is equal to pi d1 square upon 4. Okay, it is equal to pi d1 square upon 4, or we can write it as pi upon 4. Value of d1 is 4.24 centimeter square, and on calculating it we will get the value, that is 4.494 pi centimeter square. This is initial area we had got at 27 degree Celsius. Now area of the hole at 227 degree Celsius, and this area is called as A2, and this is equal to A1 into 1 plus beta delta T. A1 into 1 plus beta delta T, and we can write it as 4.A1 we had got the value 4.494 pi 1 plus beta 3.4 into 10 to the power minus 5. And change in temperature, what is the change in temperature? That is delta T, 227 minus 27, that is 200. Clear? And from here, on solving it, we will get the value of 4.525 pi. 4.525 pi centimeter square. On solving it, we will get the value of A2. Now, since we had got the value of A2 here, so since we have got the value of A2, from here we can find the value of D2, because diameter D2, the A2 is equal to pi D2 square upon 4. A2 is equal to pi D2 square upon 4, and it is equal to 4 A2 upon pi D2 square. And on solving it, we will get the value of D2 4.2544 centimeter.